Hey everyone, today we are covering Python garbage collection in two parts: when it triggers and how to tune it. First, we'll look at the two ways JS runs: automatically when thresholds are hit, and manually when you call just collect. Then we'll dive into performance tuning, adjusting those thresholds for your app, measuring the actual impact, and learning best practices. Let's jump in. Python triggers garbage collection in two ways: automatically through thresholds and manually when you explicitly call it. Let's start with automatic collection. Python watches as you create objects. Every time you create something new, Python increments an internal counter. When that counter hits a threshold, boom, garbage collection triggers automatically. Let's have a look. Watch this. As we create objects, generation 0 fills up. The moment we hit 700 objects, Python automatically runs a collection. See, it happening in real time. Objects get collected, survivors promote to generation 1, and the counter resets. Now, here is something important. That 700 threshold, that's the classic default, but as we already talked about it in the previous part, in Python 3.13 and later, as I have noticed, they bumped this up to 2000 or even 5000. Why? Because 700 was too aggressive for modern applications. Higher thresholds mean better performance. Look at the debug output. JS collecting generation 0, the seconds elapsed. Generation 0 collections are incredibly fast, 1/10,000th of a second. As we keep creating object, generation 0 fills and empties repeatedly. After about 10 generation 0 collections, generation 1 finally triggers. And after about 10 generation 1 collections, we finally move to generation 2. Okay, here it is. There's generation 2, the full cleanup pass. This takes about 20 milliseconds, 100 times slower than generation 0, but it only happens after roughly 100 generation 0 collections, so it's rare. Well, now let's talk about manual collection. Here I can create objects manually and control exactly when collection happens. Watch, I'll add some objects to generation 0, those yellow circles. Now I'll click collect gen 0, some objects get collected, survivors turn orange and promote to generation 1. I can collect multiple generations together or run a full collection across all three. This is equivalent to calling JS collect in your code. Manual collection gives you control. Maybe you just finished processing large data and want to clean up immediately, or you are about to do something memory intensive and need to free space first. Just call JS collect. Here is the code. It's simple. We are going to import GC, as you maybe already noticed, and then call JS collect. And it returns how many objects were collected. You can target specific generations, but remember that JS collect collects only unreachable, the deleted objects, not everything. So how many objects were collected? You can target specific generations by JS collect 0 for just generation 0 to be collected. Then the same way JS collect 1 for generation 0 and 1 to be collected. And when you call JS collect 2, it just collects everything. Okay, remember that, it's important. Most Python programs never need manual collection. The automatic system works great, but for large-scale data processing, long-running services, or memory-constrained environments, this control is invaluable. The automatic thresholds keep things running smoothly. Manual collection give you surgical precision, let's say, when you need it. That's Python's garbage collection, convenient and powerful. Let's talk about why you would ever need to manually call Python's garbage collector. Look at this code. Yeah, it's huge. We are processing 5 million lines of text. But we can't load them all at once. That would crash our program. So instead, we read them in small chunks of 10,000 lines each. Here's what happens. In the first cycle, the code opens the file and starts reading chunks 0 through 99. That's 100 chunks, which equals 1 million lines. For each chunk, it runs an expensive operation, in this case converting text to uppercase, and stores the result. Watch the memory usage. It starts at 25%, climbs to 35%, then 50%, then 65%. All those temporary objects are piling up in memory. Python's automatic garbage collector hasn't kicked in yet, and we are approaching 70% memory usage. Now here is a critical moment. When we hit chunk number 100, the code manually calls garbage collection. See that? Memory drops from 70% back down to 40% or something. We just freed up 30% of our memory. And then we repeat this exact same pattern 4 more times. Process another 100 chunks, memory climbs, hit the trigger point, manually collect garbage, memory drops. Over and over until all 5 million lines are processed. Without these manual garbage collection calls, your memory would just keep climbing until your program crashes. Well, but with them, you maintain steady, predictable memory usage throughout the entire job. That's when you need manual garbage collection, when you are processing large batches of data and you can't afford to let memory spiral out of control. We already know what circular references are, 2 objects pointing to each other with no way for our program to reach them. Now let's see how Python's garbage collection actually handles this problem. First, we enable debug mode. This tells Python's garbage collector to show us everything it's doing. Normally it runs silently in the background, but with debugging on, we get a complete play-by-play. Look at what happens. We create our circular references, not 1 and not 2, pointing at each other. Reference counts show 3 for each object. You should already remember why it shows 3 instead of 2. Then we delete the variables. The objects drop to 1 reference each, but they are stuck, trapped in their circular reference. We all know this story already, with no way for our code to access them. Now we manually trigger the garbage collector, and this is where it gets interesting. Watch the console output, collecting generation 2. The garbage collector starts its scan. It's examining thousands of objects in memory, looking for problems. Objects in each generation, you can see the numbers. That's how many objects it's checking across different age groups. Then comes the key moment. The output shows collectible, followed by the memory addresses of our 2 node objects. The garbage collector has found them. It's identified that these objects are unreachable from our program, even though they reference each other. And finally, done. 2 unreachable, 0 uncollectible. That's it. 2 objects collected. Memory freed. The circular reference that reference counting couldn't touch. The garbage collector just cleaned it up. This debug output is your window into what's happening behind the scenes, showing you exactly which objects got collected and confirming that the garbage collector is doing its job. I hope this video was useful for you. You can like and subscribe. And thanks for watching.